Okay. So we just finished up talking about Carnot devices, or reversible devices, or reversible. So I'll write a few things with you here because I just noticed I've not written anything for a while. We just looked at PowerPoint slides. So for reversible cycles, okay, the ratio of temperatures is equal to the ratio of the heat transfers. And that means then that the thermal efficiency for a reversible engine is 1 minus TL over TH. The coefficient of performance for a refrigerator that's reversible, and that's going to be 1 over, make sure I get this one right, yeah, TH over TL minus 1. And the coefficient of performance for a heat pump, if it's reversible, is 1 over 1 minus TL over TH. Now, this is always still equal to, these are all equal to the output over input, what you want divided by what you have to do to get it. A Carnot cycle, by definition, is reversible. Got an example here. Let's look at it. Now, I don't know if this is 699 or text. It's 6 something in the hundreds. You'll find a problem similar to this. Let us say, though, that this is, the problem statement will tell us that this is a Carnot refrigerator. Sorry, it's hard to write worth a darn. Refrigerator. Carnot refrigerator. Okay. Okay. So the problem statement would tell us that we have a Carnot refrigerator operating in a kitchen at 25 degrees C. The power input to the compressor, put a dot above that. The power input to the compressor is 500 watts. Okay. If it's operating with a COP of 4.5, determine the rate at which it's removing heat from the refrigerated space, and also determine the temperature inside the refrigerated space. Okay. Well, this one's not too bad. Example. Things that are given. We know it's Carnot. Carnot cycle, which tells us that it's reversible by definition. That's really kind of the important thing to come away from when they tell you it's a if they tell you it's a Carnot refrigerator, that just means it's a reversible cycle. And there's also information about how the processes occur then. They've told us that it is losing heat to a high temperature body, the kitchen, right, or the air outside the refrigerator at 25 degrees C. They've given us the power input, which is going to go in at the compressor, is 500 watts. They've given us the coefficient of performance for this refrigerator, and again, because it's Carnot, we know that's reversible. That's equal to 4.5. It's pretty high, but that's okay. They want us to find, what did they want us to find? They wanted you to find the rate of heat removal from inside the refrigerated space and the temperature of the refrigerated space. That's the low temperature side of the device. So they want you to find Q dot L and TL. Okay. So what are some tools I might have to find heat transfer? Well, first law will get you there somehow, right? We could draw first law for the entire refrigerator. If I knew information about the evaporator coils, I could find QL maybe that way, but I don't have any of that, okay? I mean, again, there's nothing saying we couldn't draw the first law for the refrigerator. I just call it a fridge. Right? First law for the fridge. You could draw all the devices out if you like, or we could just say, well, if I don't need to know about the individual devices inside, we could say, well, I've got a power input, I've got Q dot H going out, and I've got Q dot L coming in from the food, and this is the kitchen. Okay? The kitchen's at TH and the food is at TL. So the first law for the fridge, we add the in, subtract the out. So again, I've got power in plus Q dot L minus Q dot H. That's a cycle, so it's equal to 0. I know the power input, and I'm looking for Q dot L. Q dot L is equal to Q dot H minus the power input. So if I knew Q dot H, I could find Q dot L. So I don't think that's going to help me. So what else do we know? Well, we also know the coefficient of performance for the refrigerator. Now, again, we know it's reversible. We know the value is 4.5. But what do we know about this? Well, coefficient of performance measures what you want. What do you want from a refrigerator? What is the goal of a refrigerator? Out of these quantities, which is the goal? This guy. Q dot L. That is what you want. That's your numerator. What do you have to do to get it? What are you paying for? This guy. Electricity, the power going into the compressor, the power input. So I know this, boom, I've got something I can solve. Again, this was one equation, two unknowns. I don't know this and I don't know that, so that didn't help me. So what do we do? Well, so what do we do? Well, we go check Chegg or we go look at the solutions manual. No, what else do you know that might involve QL, or what else do you know about this device? Well, I know the COP. How does that help me? Well, it helps me here. All right, boom, we're done. I didn't have to go look anything up. So this is 4.5 times 500 watts. I think I can do that without my calculator. This is going to be 2,000. Nope. Yeah. Is that 4,500? Yeah. I'm second guessing myself, and it's just easier. By the time I work it out in my head, it's just easier to grab the calculator I got sitting next to me and say it's 2250 watts, Steve. 2250 watts. Okay, that works. Cool. What else do we need? TL. How do we find TL? Well, we could use specific heats, right? That involves temperature. No, we don't have enough information to do that. But we don't have a constant phase. That's not going to make any sense. So what else do we know? Well, we know it's reversible. We know we've got a reversible device. We know it's a refrigerator. So I can go look up COP for a reversible device because that is a function of temperature. So go back in my notes, go to the book, go pull the video, whatever, somehow go look up and find that TH over TL minus 1. And we've got this value. This is equal to 4.5. That's COP is equal to 4.5. So here we go. I've got do some algebra here. Okay. Yuck. 4.5 times this quantity, TH over TL minus 1. That's equal to 1. Okay. And what? Well, that didn't help me at all. TH over TL is equal to minus 1 is equal to 1 over 4.5. There we go. Now I'm getting somewhere. All right, next page. Do your algebra however you like. I'm going down a rabbit hole here. I can see the light at the end of this tunnel, so I'm going to keep going, but if you see a better way to do this, go for it. Not going to hurt my feelings at all. Again, what am I trying to get to? I'm trying to get to TL. What the heck am I looking for? TL. TH times this quantity, no, TH divided by this quantity. TH divided by 1 over 4.5 plus 1 is equal to TL. Okay. What is TL equal to? I'm sorry, what is TH equal to? How many of you said 25 degrees? You're wrong. Yes, it is technically 25 degrees, but what is TH equal to? Can you plug 25 degrees in here? No, you cannot. You are multiplying by a temperature. 25 plus 273 makes 298 kelvins. I can use kelvins. I cannot use Celsius here. Okay? I'm multiplying or dividing by a temperature. I cannot use 298 kelvins. I cannot use Celsius. 1 over 4.5 plus 1. Okay. 4.5 inverted plus 1. Invert that. Multiply by 298. 243.8. 244 if you like. 243 kelvins. .44 kelvins, I guess. Alright guys, I think I'm going to stop there. That's a good number of videos. I know it's going into a holiday weekend. Those of you who are actually keeping on schedule, hopefully this gets you going. There is another example in the PowerPoint notes, a little more complicated one, but I don't want to make too many videos. If you need, look at the solution. If you need help working through that one, but go through these. I've talked to you guys a little bit about. So I'm gonna go off on a bit of a tangent here because I've got 3 minutes. Okay, I'm not gonna go the full 3 minutes. I don't think. I've told a few of you guys this. You're trying to learn. I'm trying to help you learn how to solve problems. Okay, so my hope is that you're starting to get this. I understand that if I just go look at the solution and say, "Oh, I can do that," well, that's kind of like watching somebody shoot free throws and say, "Oh, I can go shoot free throws because I've watched these NBA players shoot free throws, or watched these college players shoot free throws. I watch all these videos of people shooting free throws. That means I can go shoot free throws." No, it does not. Same thing when you look at a solution and say, "Oh, I know how to do that." It's like watching somebody shoot free throws and say, "Oh, I know how to shoot free throws." Go shoot free throws. Go actually solve these problems before you go look at the solution. If you go look at the solution, you're literally just watching somebody shoot free throws. You're not actually learning how to solve these problems. So where should you go check the solution? Here. That would be okay. You can check the solution here. Although you've not quite figured out how to get TL yet, right? So, I mean, you could check the solution here, but just understand you don't know how you're going to get TL yet. So, before you actually do this calculation, say, okay, well, how do I find TL and try to find that? So once you've got, and ignoring this line here, you could go check at this point, right? You've got an expression here that you know you can do enough algebra to solve. You've got an expression here that you know you can solve. And all you got to do then is just run this through a calculator, and here you just have to do some algebra. You know this, you're just looking for one unknown. That's when you could go actually look at a solution. If you look before that point, you're looking too early. You're watching people shoot free throws, which is not going to help you. Okay? So just keep that in mind. I hope that helps. I know I use that analogy too many times, but I really feel like that's very effective because most of us have probably shot a free throw in our life, and you probably understand that watching somebody shoot free throws does not help you shoot free throws. Watching me work this out, looking at solved solutions and saying, "Oh, I can do that," that doesn't help you. You're not learning how to do this. Go do it, and then check it against a solution. Okay? And anytime you want to do it on an example, when I display the example problem, if you want to pause and try to work it out at that point, that would be really good. If it's your first problem you've encountered of this type, maybe that's not the best idea. Maybe then, you don't want me to just hand you a basketball having never seen somebody shoot free throws and try to shoot free throws. Maybe watch me shoot a couple and then say, okay, let me try that. But, if you're comfortable that you can do it. And another thing is go back and watch these videos later. And when you hit an example problem, pause then and see if you can write out a solution. Okay, I've gone the whole time. I'm going to quit there. You guys have a wonderful holiday weekend, or I hope you already had a wonderful holiday weekend, whatever the case may be. Guys, be careful. Come back with all your fingers and toes. Don't blow anything off. All right, guys, be careful out there. Stay safe, stay healthy.